Okay, I can skip the first ones. In this presentation, I use a lot of references. I didn't actually put the references there, I've changed it so many times. But these are the articles I have used when I've been preparing the presentation, and also some of my own research. The first two ones are general academic papers about big data and data exploration. The three next ones are actually written by researchers from Oracle. They are still quite generic papers, but they are more about Oracle perspective, especially the JSON thing. And the last one is about data guide, which is in 12.2, one of the cool things about JSON. So if you're interested, these are quite interesting articles to read. So, very briefly about the history of data models. So, the database is for storing and retrieving data. That's what it's always been, and I think that's what it always will be. We had the network data model. Some of you might remember this kind of thing. We had the hierarchical model. We had all kind of different kind of models until the relational data model came. And that's been kind of de facto since that. I think the reason for relational database being the best so far is that it has a solid theory. So it's not just something somebody invented and started to use. It has a solid theory behind it. So it's a very solid thing. It's a standardized environment for the storing and retrieving data. So I think that's why it's so popular. But it was not enough, because the evolution of software development and programming languages has led to all kinds of new demands for data models. Some of you might remember objects when they came. The object databases were supposed to rule the world, and relational database is dead. That was like 20 years ago, and it didn't die. The object databases were created to be able to naturally, natively use objects, saving and retrieving objects. In the end, these functionalities we added to a relational database, and we have so-called object relational database management systems. Oracle is one of those. Then we had XML. So these are just some examples. There are plenty of other things as well that happened. XML was for transferring data in a standardized way, and we needed to have a system to save and retrieve XML documents natively, and XML databases were created. Later, these features were added to Relational Database Management System, and Oracle is one of those that supports XML. We have the XML type, methods for that, SQL functions, indexing, and we can even register XML schemas. Spatial came. We needed to have a way to save and retrieve spatial data easily, and spatial databases were created, and later these features were added to a Relational Database Management System, including Oracle. Then, after that, I would say we get something that was not just about a programming language and being natively able to do something. We get FSD, which is flexible schema data. In the relational world, we typically design the database first, so we have the schema first, and after that is done, the data is allowed to come into the database. But the new world, FSD, says that we need to have the data first, so we save it as it is, and when we are querying the data, we have the schema. If we never query the schema, the data, we will never have a schema. So that was a different kind of change for the demands. That was called NoSQL. NoSQL is one of those words I hate again. So it seems to be all the new words I don't like this word, but I don't like this word. I think NoSQL is a crappy word. So it actually means nothing. It means it's an umbrella for different solutions to different problems. And this thing is just put under one umbrella, which is called NoSQL. Those special purposes and solutions are document stores, key value pair stores, column stores, and graph stores. And together they are called NoSQL. These databases, they don't have ACID, what we have in relational, the atomicity, consistency, isolation, and durability, they might have a thing called base, which is basically available, soft state, eventual consistency. My favorite example about base is Twitter. So it's okay. So neither of these is the exact answer for anything. So you just have to understand there are two different things, acid and base. And depending what you need, either of these might be the right solution. So I'm not saying that base is bad and acid is good. I'm just saying they're different, and you have to understand when to use which. So in Twitter, we use base. And it's normally very good because it's enough that it's eventually consistent. But in my use case, in this particular case, I was in a conference, and every morning we had a Chinese exercise, Qigong or whatever it's called. And this guy who was giving the class, he always tweeted in the morning what time and where we meet. Every morning I went there, I did my Qigong, and then one morning there was no tweet. I was thinking, okay, the party was quite long, so maybe he stayed up too late and he's too tired to have the exercise this morning, so I just went for breakfast. I'm having my breakfast and he shows up and he's like, how come you didn't come for the exercise? I said, well, you didn't tweet. I did tweet. So he's from US, in a US node. I'm in Finland, European node. So we're in different nodes in Twitter. And he said, I did tweet. I said, no, you didn't, because I specifically checked and there was no tweet. And I opened my Twitter and here it comes, like a new tweet. But the exercise was already gone. So for me, this tweet came too late. But I can't say that it wasn't eventually consistent because I finally get the tweet anyway, even though it was too late. So usually with Twitter, it's okay to be eventually consistent, but in my use case, it was not okay because I missed my class. But that's the difference between acid and base. They are different strategies. Both are okay if you understand why you chose whatever you chose. Also, the need to scale up, which we are doing with our relational databases, and the scale out, which was a new demand from the business. We need to be scaling out. Like Hadoop boxes, we have to be able to put more Hadoop boxes on a row. So these were the kind of new things that were introduced to us. The document stores, JSON is the most typical one. For JavaScript programming, like a version of XML, we needed to be able to save and retrieve JSON documents natively. Well, this is supported by Oracle, by the data type CLOP and NCLOP. It's fine, but it's not completely natively supported that way. But there is a place for this kind of data. Then key values pair stores is something between semi-structured and text. The key is structured, but the value is text. This is supported by Oracle Database, but it's also supported by Oracle NoSQL. So Oracle NoSQL Database is key value pair store. Then column stores, it means that the data is not stored in rows, it's stored in columns. Typical example from Oracle is in-memory columnar store. The graph stores. A bit confusing because graph stores are all about relationships. Earlier today we were talking about relationships. We're talking about entities and relationships. So you would think that relational database is the relationship database. But actually it's not. It's graph store. So graph is about relationships, totally about relationships. It's for finding information like fraud detection and how people are related to each other. Is there something fishy in their relationship and so on? So the kind of queries you can do from graph stores, you are not able to actually get from relational database. That's why graph is quite interesting. So it's about nodes or vertices and about links and edges. Each vertex and each edge has collection of key value properties. And a graph can be easily created from relational model automatically, which is quite great. And this is supported by Oracle Database. And I think this is the most interesting thing about those NoSQL things. Everything else I think is boring, but this is very exciting. And it would be worth of its own presentation. Now I just briefly mention it, but this is something I would keep my eyes on just in case, because this is going to be something in the future. So NoSQL Slowly, these features were added to the relational database management system in a way or in another. But you already see the pattern. We have a new thing, we have a new database, and finally we add that to a relational. We have a new thing, a new database. So it's the same pattern all the time. And what's the point? Why are we always doing the same? So what's Gartner saying about this? Gartner is saying that operational database management system use cases have expanded beyond traditional transactions. So the transactions we are trying to do now are not the same we've been doing before. So as I said in the first presentation, we need new ways of doing things. The big data. And relational operational database management system products and emerging NoSQL and multimodal offerings are entering the market to address some of these new use cases, creating opportunities for best-fitting engineering but threatening established company standards for information management. It also says that vendors, blah, 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 two-way portfolios creating both multimodal and multi-product choices and confusion in the minds of buyers. It means that you decided, I want to do that big data too. You go to a vendor and you said, I want to do big data. What is my product? And instead of really giving you the product, they give you two products. Try multi-product or try multimodal. And then you go to the next vendor who's doing the same, and the third, and the fourth. So not even vendors know what to do. So how would you know? So going to the big data world is not that easy. So what does Gartner recommend? They say that first you have to identify the use cases you have under consideration. So first, understand what you want to do. And then evaluate potential alternative product selections. So do not go to the vendor first. First think, what do we want to do? And then go to the vendor. You already know what you want to do and see if they have a product for your purpose. Issue RFPs, maybe, but at least update your standards, training, and support organizations to manage, qualify, and accommodate additional requirements if your technology portfolio is expanding. So I am very sure this big data world will bring you new technology in the house. At least inside Oracle, there will be new features you haven't been using before. So you need to update your standards, your training, and your support organization so you will be ready for the change. Their predictions, assumptions for the future. By 2017, all leading operational database management systems will offer multiple data models, relational and NoSQL, in a single database management system platform, which is true. Oracle is doing that, and many other vendors are doing that. Through 2018, 50% of small operational database management system vendors will disappear due to acquisitions, mergers, or business failures. That's sad news, but probably true. There will be companies going away. But the last one is my favorite. By 2017, the NoSQL label will cease to distinguish database management systems, reducing its value and resulting in the label falling out of use. So we will still have those technologies available, but we don't call them NoSQL. I like this thing. I hope it will be happening. And I think it is happening because, yes.
I do think this
yes,
is already happening.
It is happening. We hear that less and less. And it's great because whoever invented the name, oh goodness. So the big data, as we already spoke earlier today, brings more than just the need for new data models. So this time we just do not manage by adding new data models in a relational database management system. We have to do something else as well. As we spoke earlier, it's not about just the size. It's about the size, the volume, but also about velocity, variety, veracity, viability, value, variability, and visualization. So it's about many factors that is in big data. So not just the new data models, but also different things. And the volume and velocity, that's quite okay. We are used to that already. So we have like telephone operators, they have a lot of data coming in. So it's a big volume, speed is very, very high. That's fine. We are okay with that. No problem. We have solutions. But then we got this variety. The different data models, different data sources, different whatever. And that leads to diversity and complexity. And the problem is that now that we have all these different data models, users cannot query all of this data using just one query language. They have to use different query languages, they have to implement their own join algorithms to join those different sources. And also, many of those specialized systems are lacking some features that we take for granted. Like we just talked about ACID, we take that for granted, even though we know that they probably don't have it, but we still expect that because we are used to that. But also things like security, fine-grained security, how to do the backups, and especially the recovery, this kind of things. So, and about big data a little bit more, it's not just about saving all that data. You remember it was also retrieving the data. Data exploration is the retrieving part, but it's more complex than just the regular retrieving data, because data exploration is to efficiently extract knowledge from data, even though you do not know what you're looking for. So it makes the query more difficult. You can't just say select whatever, where, what, blah, 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 so on, because you don't know what you're looking for. Exploratory computing is a conversation between a user and a computer. And the computer should be helping me actively with my finding knowledge. And exploration process is investigation, exploration seeking, comparison making, and learning. Both ends of the computer. And we need a lot of techniques to be able to do that. We need statistic, data analysis, query suggestion, advanced visualization tools, the machine learning we spoke earlier today. Many, many techniques to be able to have this kind of conversation. But just like machine learning, this is not a new thing. 1977, this guy, J.W. Tokey, wrote a book, Exploratory Data Analysis, where he says, with exploratory data analysis, the researchers explore the data in many possible ways, including the use of graphical tools like box plots or histograms, gaining knowledge from the way data are displayed. So, very old thing again. So, all those problems we spoke earlier today, volume, variety, veracity, not all data is reliable, we must be supporting non-technical users, and everything must be done fast and efficiently. It's done in different layers. We have the user interaction layer, or the user interface, we have the middleware, and then we have the database. For the user interaction, we have a lot of challenges, because this interface should be helping me to find information from the data without even me knowing what I'm trying to find. And when we find something interesting with my computer, the computer should just suggest new things based on what we just learned. So it should be very nice conversation, learning more knowledge based on what we already learned. This data is in different formats, large amounts of different kind of data, and it takes time to analyze that kind of data, even though we knew what we are looking for, and now we don't even know. But still, it has to be a very fluent conversation, because I won't wait here for hours for the computer reply. So it has to be a very fluent conversation. And remember, not all users are IT professionals, so it cannot be any kind of SQL or something like that. The conversation must be a natural conversation, easy for non-technical people. So the visualization is very important to support this conversation. About the visualization, visualization is important because one picture tells more than 1,000 words. And for human eyes, it's much easier to understand a lot of data when it's in a picture. Often when we talk about visualization, people think it's only about the query result visualization, but it's also other things. These visualization tools should assist users to navigate in the underlying data structures. They should incorporate new types of interactions, such as collaborative annotations and searches. It should help query result reductions like aggregation, sampling, filtering operations, and then of course show the result as a visualization. Also, it's not easy because user involvement is a big factor. So one answer can be very relevant to me, but not relevant to you at all. Actually, for you, it might be very annoying. So the computer should understand what's interesting to me and what is definitely not interesting to me. And some possible techniques for that is grouping. So the users are grouped in groups. Then classify different notions of relevance. Very relevant, not so relevant, very annoying, this kind of things. And devise strategies to customize the system response to the user behavior. So whatever I respond, it should learn from my response. Next time, she won't like this, so I don't suggest it again. Then we go to middleware. It seems that middleware is easy because whatever we do in middleware, we don't have to change the architecture under middleware. That could be true, but there is no silver bullet for anything. Two techniques that can be used is data prefetching and query approximation. Data prefetching, we cache data sets that we think that will mostly be used. Of course, the problem is how do we know what data will be used, so what to cache. And it's of course a trade-off between introducing new results and reusing those cached ones. So it's not that we should be prefetching everything, it's something we need to think carefully. Query approximation, it's very much based on samples. And to be able to have query approximation, we need to have good sampling techniques. So the system, instead of giving correct right answers, is giving approximate answers. And the reason is that we get them very fast, and they get a little bit of clue, should this be interesting or not? So it's not giving the right answer, but it's kind of telling you a hint if this is something I should be investigating more. And it's a trade-off, of course, between result accuracy and the query performance. Then we go to the database, which is, of course, our favorite in this topic. So it is about saving and retrieving data today and tomorrow. So the way the data is stored defines the best possible ways of accessing it, and the way data is accessed defines the best way to store it, right? But now we have two small problems here. We don't know what data we will have, and we have no idea how it will be used. So the two pieces we needed are missing. We don't even have one of these pieces. So how do we save the data so it's saved in the best possible way? We can't. So there is no way of knowing the best possible way of storing data when we are loading it and saving it. And we don't know what we are looking for from the data. So we don't know anything about the queries. So we can't have the best possible way of storing it. So how can the architecture of database systems be redesigned to aid data exploration tasks? Well, in the saving, it has to be done efficiently and reliably. We have to understand the data when we are saving the data. Maybe find the primary keys to be able to join data with other data we have. Taxonomies to understand that first name is actually, my relational database first name is actually the same as F name in a JSON file. Something like that. So metadata management, to understand the data. We need to be categorizing things, like some data is more valuable than other, some is more reliable than other. Not all data should be stored in the same place. So when data is stored, should it be in my Exadata or my Hadoop or my where? And also classification in all its forms. So when we are saving the data, we should understand it. And of course, we can't do it manually because remember the speed? So we have to classify it before we save it, because otherwise we will just have a lot of data in the database and we are not able to use it when we finally want to use it. And sometimes we even might need to transform the data when we are saving it, who knows? We might know that this format, whatever it is not going to be good for the queries we will have if we know something about the query. So we might even need to transform it. And usually the space is expensive, so we might define a place to store it. And we have to maybe decide if this data should be stored close to the other data or very distant from it. The cat videos here, cake recipes here. And then the problem about classification. We just classified the cat videos are not important. We put them here. But suddenly it becomes the most important data we have because we only want to address customers who are posting cat videos because we expect them to be cat friends. And we want to address to customers that are friends of cats. So who are the ones who posted cat videos? So suddenly this data becomes important to our business. And then small tiny little example about date types. Actually Sten mentioned the same thing in his presentation. So what do we do with dates? In a relational database we have no problem. There's the date data type, we know exactly how to read and what to do with it. In the JSON we got date coming in. Is it day, month, year, or month, day, year, period? What kind of symbol? Does it have the time also there? And so on. What about if it's a text file? The same questions again. So how do we understand what the date really is? So when we are saving the data, we have a lot of problems understanding what we are really saving. What's the point of saving a date we don't understand? So quite often the solution for saving a new data model is CLOG, BLOG, external table in Oracle. So we do have places where we can save them now that we understand what we are saving. But that's not enough because we have those demands for the fluent conversation, remember? And finding knowledge we don't know about. So we need a lot of adaptivity and we need flexibility. We need adaptive indexing, adaptive loading, adaptive storage, flexible architecture, and architectures that are tailored for approximation processing and sampling. And it's so funny because this is actually what Larry was speaking in his autonomous database. These are the things. So I already can say that if you have Oracle database, you are quite good with this multimodal database because a lot of these things we already have in Oracle and there's so much more coming. So they are really in the edge of this. So adaptive indexing means that we are creating indexes incrementally and adaptively while the queries are in process. We know which columns, which tables, which value ranges and so on are used, and the indexes are fine-tuned based on that knowledge. Indexes are built gradually. As more queries arrive, indexes are continuously fine-tuned. That is what is adaptive indexing. Adaptive loading can mean something that a person can define what loading is. So, because not all the data is needed, users might want to leave some parts of the data unloaded because it's not needed. And because not all data is available, users might start querying a database system before all data is loaded. So it should be quite adaptive. The storage. There is no one perfect solution, as we already agreed earlier. But this adaptive storage can be used for different needs of storage layouts. There are some examples here I listed, but in Oracle we have in-memory columnar stores and we have real-time materialized views. Actually, the latter one was introduced in 12.2, also an interesting feature. And the best thing about these adaptive things is that we don't need, the two last ones, is that we don't need to have disk space for them because they are somewhere not in a disk. So it makes it a little bit easier because we are talking about big amount of data. If we need to save it twice or 3 times, it will be too much. The flexible architecture can be tuned to the task at hand. We can, by having a declarative interface for the physical data layouts, by having a declarative interface for the whole engine, and using organic databases to continuously match incoming data and queries. So we kind of start with a schema that is good enough and we evolve it during those loading and queries. So the architecture that is tailored for this kind of processing, sampling-based query is the key word here. So we need to be efficiently accessing and updating those sampled data sets. Of course, the first question is, what kind of sampling algorithm to use, because this sample should be a good example of the whole data. How do we know it is a good sample, because most of the data is still coming in? So it's a question as itself. But also, we need to be able to access and update it. This should be in the database core. And for example, in Oracle 12c, we have adaptive dynamic sampling, which is an example of this kind of things. But I think that designing new engines is one of the open challenges we have. So engines that will be supporting this kind of behavior is still to come. Anyway, we do have techniques for large data sets. We have summarizing, data mining, histograms, and effective pruning techniques that can be used for large data sets. But about those data models, so we have those different data models, and that's a fact. There's two possibilities we can do with them. We can have a polyglot persistence, or we can have a multimodal database. Polyglot persistence means that we have different kinds of data models, and they have all different kinds of data stores. So we have one for relational, one for this kind of NoSQL, one for that kind of NoSQL, and so on and so on. So very typically when I go to a customer who's using NoSQL, it means they have several databases, because like I just explained, NoSQL means different things. So they have different brands. So you have several technologies in the company. How do you use that data? And where do you get this kind of competence to actually understand all those technologies? So even using Oracle technologies, being just Oracle customer, you are able to build a polyglot system. You can have a Berkeley DB as a key value store. You can have an Oracle NoSQL database as a key value and sharded database. You can have Oracle Timestamp as an in-memory database, Essbase for analytic processes, of course Oracle database for relational, and so on. So you can have a polyglot build with just being Oracle customer. But the problem is with polyglot that all these different systems, they have their own different language. They have their own front-end user interface. How do you join the data between those systems? How is the data consistent between them? Is it secured? And where do you have all those skills to understand all those different systems? So this is how they're different. This is polyglot. We have different systems for different purposes. And this is multimodal database, where we have one single database that is hosting all your different data models. I will wait for the photo. So the multimodal database is designed to support multiple data models against a single integrated backend. And the idea here is, when somebody invents something new again, we are already ready for whatever comes. This will already manage whatever comes. We don't have to invent a new database XYZ. It will be implemented in here. We only need one query language. We can have several query languages for different data models as well, but we have one query language that can handle all the data. All the data is available in one place. We can have ACID, we can have base, we can have whatever defined for each data model itself. So we can have one data defined as base, another data defined as ACID, depending how we want to do it. So in fact, we have all the good things from relational world added with all the good things from the new world in one place. And still, it's about how to save and how to retrieve the data. But it's done only with one and one. We already spoke about this one when we were talking about when we are saving the data, what do we have to think about? The categorizing and so on, understanding the data. But for the retrieving the data, we have some interesting solutions from Oracle. We have JSON data guide that was introduced in 12.2. The idea is that we save JSON as it is, and we use it with SQL. And actually, this is exactly write without schema, read with schema. So we are making it possible to have flexible schema data management in a relational database. In this case, it's only for JSON, but of course it can be enlarged to other semi-structured data types as well. So we are storing JSON objects as aggregated self-described entities, native JSON, without threading it into relational rows and columns. We can index it using schema-agnostic strategy to support ad hoc queries that search both schema and value together, which is valuable for us. We can query JSON using SQL, or we can use SQL JSON path. So what is this data guide? There's two forms, there's persistent and transient. Persistent is a component of a schema-agnostic JSON search index. Transient is a new SQL aggregate function over any JSON collection that can be computed from SQL declaratively. The persistent, as I said, is part of the search index infrastructure. This is how it's created. The content of data guide is automatically updated whenever the index is synchronized. And when you're defining these, well, I will explain it later. And and when the index is synced, everything that's been updated is added or updated, automatically updated there. But if anything has been deleted, it's not updated. So you must create the index again if the deletion is important. Usually it is not, because typically JSON, we don't delete anything, we just add new things. So I think this is probably not a problem, but it's just good to know. Deletions are not updated automatically. You can also include statistics, how frequently each JSON field is used in the document set if you want to. Explicitly gathered and not updated automatically. So the transient is not updated automatically. And it's created by scanning the JSON documents. For these data guides, there's two. There's flat and hierarchical. So flat is just to query data guide information such as field frequencies and types. But the hierarchical is you can create a view on top of JSON files, or several views, or you can add a virtual column. And in this particular case, I think that the best thing is that if I have this F name as a field name in JSON, in my view I can call it first name, like in my relational table, and it will be easier in my queries to just, this is not really a column that I will be joining, but let's pretend it's a column I would like to join. It will be easier to join because it will have the same name as my relational has. So in the view, I can call them with whatever name I want to. I don't have to use the name that is in JSON document field. In my view, I can just call it with whatever name I want to. And it makes my queries a bit easier. So I can have those views, several views if I want to. It can be based on hierarchical data guide or path expressions when I'm creating views over JSON. I can have those virtual columns. And the reason I think data guide is interesting, I don't go to details, but I put everything there. If you're interested about the topic, you can go and test those DDLs. Because it enables the flexible schema data management. Now it's only for JSON, but in the future it could be for anything that is semi-structured. The same thing could be implemented for something new. Remember when we had XML, we had XML data type and so on and so on. It was treated as special case XML. But now JSON is not done the same way because JSON doesn't have its own JSON data type. It just has the place where it can be saved, and then it has this kind of layer on top of it where you can handle it as it were relational. So then we have the next thing coming in, XYZ, whatever, and actually it can be, exactly. So we can just use the same system and have it in relational database. We don't have to build anything new. And I think that's very exciting about data guide. And actually, it is not something that Oracle invented last year or this year. It's been built for 10 years. the idea behind it, it's been maturing for 10 years. Because I know the guy who invented it, and he said he's been building it for 10 years. Of course, it was not for JSON when he started it, but the idea was, how should I treat semi-structured data? And this is what he came up with, and I think this is extremely cool. And I expect something great related to this. Another thing I like in Oracle related to this multimodal thing is in memory. Because we can save the data as it is. Okay, we try to understand it as much as possible when we are saving it. But we can kind of copy it to a faster data model that is kept in the memory. So if we know, or our machine learning algorithm knows, that this kind of query would do better if we have it in columnar store, it could just put it in a columnar store in the memory and query from there and give you the result very fast. And we don't have to save it twice because it's only in the memory and it's gone when we don't use it anymore. So we don't have to copy it physically several times. It can only be in the memory. At the moment, it's only for columnar store, but why not in the future something else? Very, very interesting for this retrieving data part. Save as it is and use it in a different data model in memory. And it should be very fast to build this kind of other structure in a memory. It should be synchronized automatically. And the good thing is we don't need any additional storage for it. And the version of the data model, this one that we have in a disk and the one that we have in a memory, the version that helps best that particular query is used. So maybe this could be for graphs in the future, because graph is the one I would look for first, because it gives the ability to query things we are not able to do at the moment. So if we have my relational here and then the graph here in the memory, that would bring a lot of benefits. So we do have a lot of data models so far. We had the network, hierarchical, relational, objects, XML, spatial, NoSQL, plenty of things coming. Of course, there's something new coming. There's no question about it. Of course. And then we have this demand for flexible schemas. We had all the V's from big data, giving more confusion for our multimodal. We have data exploration that is giving pressure for the fast and efficient discussion and between me and the computer, finding knowledge from data I probably don't even understand I have, and then finding more information based on what we just found. And this is given a lot of pressure, user interface, middleware, and database, all of those layers. Of course, it can be solved with polyglot solutions with different products, but that, I think it's stupid. And that's why I think we need multimodal databases. And I haven't decided which one is the right way, together multimodal or multimodal. I don't know which one is correct, so I put it differently. Nobody knows what's the correct version. I have seen it written both ways. So to confuse you, I sometimes write it like this and sometimes the other way. From Oracle, there are promising solutions. The data guide I mentioned and in memory, and these are for retrieving the data. So I think these are quite promising solutions. But there are also adaptive things in a database that are very interesting. And of course, Larry's announcement about autonomous database is very good for this world. There's plenty of research going on in the area, but the problem is that we actually need all the results already. And when the result comes from research, it takes a long time before it's really implemented. So it would be nice to have all that already, but we don't. But there's more and more coming every day, so probably we will do good already, but we will do even better in a year or two, I think. But I think we do not survive without a multimodal database because we need to have one place for our data. It doesn't have to be physically one database, but it has to be one database that is managing everything that is under it. So all our data should be managed from just one place, wherever it exists. Otherwise, it will be a mess and it will be a polyglot. Thank you so much. Any questions, happy to answer. And you already know where to reach me. Thank you.